Hello there. In this video we will be going through the convolution integral. The aim of this video will be to try and give you an intuitive understanding of the convolution integral. The convolution integral is important and is seen throughout the engineering and technology fields, and many more fields. It is used to help analyse and model linear systems, such as this example linear system, where we take an input signal, f of t, where in this case we arbitrarily say t is time, so we take f of t, and f of t interacts with this system, which has a transfer function, g of t, and it outputs our response, which we called h of t. So the question now is, how do we work out the response, which is the interaction of f of t with g of t? Well, this is precisely what the convolution integral is for. So to work out the response of our system h of t, we take the convolution of our input signal f of t with our system's transfer function g of t, and to work out the convolution between these two functions we use the convolution integral. It is important to note that we are integrating over a substitute domain, which in this case we call tau. So we're not integrating over the domains of our functions, which in this case is t. We are integrating over tau. And inside our convolution integral, we take a sort of sliding window of f, which we call f of t minus tau, and we multiply that with our transfer function, g of tau. This is a little bit of a mouthful, so let's use a slightly more realistic system. A system where we start at time 0. Now, to compute a response at time t, or for our system to have a response at time t, it is unrealistic for the system to be dependent on information and signals which has happened in the future. That is to say, we do not expect the system, or we do not expect the response of the present to be dependent on stuff which has not even happened yet. So to account for that, we set our upper limit of our integral to be t. So to find the response at time t, we set the upper limit of our integral to be t. So now for the crunch part of the video, which is to try and give you a more graphical intuition of what is going on inside the convolution integral. Let's graphically describe our sliding window function, f of t minus tau. Let's use an example signal for f of t. Let's use a triangular pulse as f of t, and a triangular pulse looks a little bit like this. And let's arbitrarily finish it at time big T. Now then, we'll need to get our triangular pulse from being in the time domain to being in the tau domain. Well, when we transform it from the t to the tau domain, it actually looks exactly the same. So it looks like this, still finishing at time big T. Now then, if we go back and look at what we're trying to do, which is trying to get f of t to be f of t minus tau, operating in the tau domain, we need to turn this signal, or transform f of tau into f of minus tau. So to graphically describe that, we mirror our triangular pulse, or mirror our input example signal, and a mirroring of a triangular pulse looks like this. At minus big T, Now to complete this and get f of t minus tau in the tau domain, we shift it by t. And to shift from f of minus tau to f of t minus tau, we shift it to the right, and it looks like this, where it starts at time or tau t minus big T and finishes at t, whereby we have shifted it from finishing at 0 to t. Now we are ready to graphically represent our convolution integral. Now remember that the convolution integral is the integral of these two functions, f of t minus tau multiplied by g of tau. So let's set an arbitrary curve as our transfer function g of tau. So we'll want to graphically represent the multiplication of f of t minus tau with g of tau, and that will look something like this, whereby we first start off at some high point on the y-axis, because that is a multiple of these 2 points, and we will finish up at 0 at tau is equal to time t. And the curve will look something like this. So now to find the integral of these two functions, we take the area of this curve between tau is equal to 0 and tau is equal to t. So what have we just done? We have shown that the convolution of f of t with g of t is graphically depicted as the area underneath this curve which is the multiple of our transfer function with a part of our sliding window of our input signal. Or to put this another way, the response of our system at time t is graphically depicted as the area underneath this curve. And that is the conclusion of what we wanted to show today. Thank you for listening, and I hope you found this video useful in giving you a more graphical intuition behind the convolution integral. If you found this video useful, please subscribe to my channel by hitting the subscribe button. The next video will be a worked example.